Okay, welcome to the AccelerEyes webinar. If any of you have problems hearing, let us know and we'll make sure that you're able to connect. My name is John Melanakos. I'm the CEO of AccelerEyes, and we are excited to have so many of you join us today and to discuss Maximus applications. And by Maximus, that's a new terminology that NVIDIA has introduced over the last several months, which enables GPU computing for speed along with GPU visualizations, specifically for high-end scientific visualizations. So we're going to discuss that concept today. At AccelerEyes, we've recently transitioned into a new product called ArrayFire. When we originally announced this webinar, we did not have ArrayFire. It was not publicly announced, and so previously we had a product called LibJacket. LibJacket is phasing out. It has given way to a new programming model that we're excited about with ArrayFire, and so I'm going to introduce ArrayFire with a few slides at the start of this webinar, and then we're going to follow up. I'm going to have Gallagher Pryor, who's our CTO. He's going to walk through some code and actually run some Maximus applications that he has built and show really what you can do with GPU software today. So to get started, essentially our company is entirely focused on GPU software, and we really are focused on the problem of making code easier while fully exploiting the performance benefits. So we don't want to sacrifice any performance for our productivity, but we want stuff that's much more productive. And so we really have two GPU software tools that we deliver today. ArrayFire is the one we'll be discussing in this webinar. It's the world's largest and fastest GPU library. It supports C, C++, Fortran, Python, and other front-end languages. It has backends for both CUDA and OpenCL, so it's hardware vendor neutral. We also have Jacket, which is specifically focused on MATLAB code and integrates with MATLAB, requires MATLAB to run. It also has both CUDA and OpenCL backends. We've been doing this for nearly 5 years now and have all across the map of science, engineering, and financial computing applications, real speedups have been delivered through those two tools to name brand and household name companies. You can see a selection of those here, and we find that so many science, engineering, and finance applications can benefit from the exploitation of the data parallelism that's inherent in their algorithms. I want to start by showing ArrayFire and just giving you a taste of what it is to write ArrayFire code in C++. In this code, it's a very simple example, self-contained in this one file. It's about 10 lines of code. What we're doing here is we're simply estimating the value of pi. We're trying to compute the value of pi sort of from some random samples, doing a statistics calculation here. And all you do to estimate the value of pi is you sort of create a bunch of random samples and then look at the proportion of those that fall inside of the unit circle. Let's see, I see some people with voice or connection problems. If in your WebEx you can sort of look at the teleconference join numbers, there's a toll-free dial-in number that you can call into, and that will help you connect into the conference phone. But you'll need to use a telephone to hear the audio. Let's see here. I'm actually going to make Bill Stott a panelist. Bill, if you could send a chat message to those who cannot connect, and they'll be able to connect here. through the audio. They can't hear what I'm saying, I guess. Okay. So while we're waiting for the connection, or while those other people are joining us, I'll just move ahead. So this code shows, again, just a simple algorithm, and we're going to show the syntactic flavor of ArrayFire. So you simply include one header file, and there's one namespace, the AF namespace, that you can use. And then you have access to a new data type in C++ called array. And you can define arrays. So here we're defining in green, the X and Y arrays, which are randomly sampled vectors on the GPU. There are 20 million samples in each of those vectors. And then any operation, any subsequent operation that you do with the array variables, X and Y, will be performed on the GPU using ArrayFire's runtime underneath the hood. So you really, all you have to do is define new data types as this array class, and any subsequent functions that you run will run on the GPU. So we've defined X and Y as array variables, GPU array variables. Then on this line of code, we're going to do some basic square root and vector multiplication and summation. And this is the actual arithmetic that computes pi. And then the blue variables are CPU variables. So when you do this operation and store it back in pi, that actually moves the result from the GPU back to the CPU, and you can of course printf the result back out to the screen. So again, just to repeat, very simple inclusion of a single header file, a single namespace, and then very simple declaration of array variables gets you out onto the GPU. And then once you're out on the GPU, you actually have several variants of the array container that you can define. You have real double precision, real single precision, Booleans, complex double and single precision are all available in these array containers. The array containers also support vectors, matrices, and volumes up to ND data type support to really make it as easy as possible to manipulate data on the GPU. Indexing and just matrix manipulation on the GPU is very difficult to do in CUDA or OpenCL yourself, and so we make that very easy with ArrayFire. So you can index into these using simple indexing keywords. End and span are some of these keywords which pull out a full column or row or slice of a matrix or volume. And again, at the end, you do whatever arithmetic you do on the array variable will automatically occur on the GPU. ArrayFire will automatically construct very nice GPU kernels for your problem and execute those and return the results into either CPU variables, or you can continue to define other GPU variables in your code. So that was C++. We also have Python, Fortran, and C interfaces. The same concept. You define an array data type, and then from there you are able to work with these array variables, these GPU variables, and any functions that you run on them will run on the GPU. And if you want to come back to the CPU, you simply cast your data back to the CPU. Once you have these array variables, there's a lot of things you can do. The main point of this discussion is going to be how can you visualize these array variables, and we'll talk about that shortly. But I want to just touch on a few other things that you can do with array variables from the compute perspective. So, for instance, you can use the G for loop contained in ArrayFire to do highly parallel for loops. So here I show a standard for loop for doing matrix multiplications. This in CUDA would require 3 kernel launches. So in each iteration, you're sequentially going through and multiplying a slice of A by a matrix B. With G4, we are able to take that full operation and put it into 1 kernel launch, which is gives you much faster and better performance. Let me explain that further. So looking at the serial case, again, what it's doing is sequentially going iteration 1, performing a iteration 1's matrix vector multiply, iteration 2, and iteration 3, all happen sequentially. With G4, we're going to do all 3 of these computations in 1 pass. And the way it actually occurs is you think of the iterator as extending this matrix multiplication problem into the next dimension. And so what that looks like is, what if you were to sort of stack each of these matrix vector multiplies on top of one another? Or rather, what if you were able to sort of construct this as a volume getting multiplied by a vector? That's sort of the way you can conceptualize what's occurring with G4. Is G4 automatically takes the body of the loop and vectorizes it so that you can do one big data chunk for all iterations getting processed at every step of that body of the for loop as one big data set. So G4 runs the body only once on the CPU. Again, it constructs a larger data set of all the data required for all iterations and crunches it in 1 pass of the body. And so what you might see on the console output, for instance, if you were to just display the iterator variable on the CPU, you would see that the thing iterates 3 times through the body of the loop, while on the GPU it actually only iterates once through that body. And so it doesn't have the overhead of launching multiple GPU kernels. You can think of G4 alternatively as sort of syntactic sugar to write vectorized code in an iterative style. You could do all of G4's body of a loop sort of without a for loop. You could just sort of rewrite the whole thing to be vectorized yourself, but then you lose the iterative style, which is conveniently expressed with a for loop. So that's really the nice thing about G4, is it lets you write in a natural iterative style, yet achieve vectorized code, which is much faster than sort of serial or sequentially launched for loop code. So that's the first feature. When you have an array of ArrayFire, you can use G4. Another big feature of ArrayFire is that when you have an array, it's very easy to scale up to multiple GPUs. And in this example, I show a simple snippet of code wherein you define an array. We'll call this Y. And all we're going to do is, in this body of the loop, we're going to create random arrays of X and run FFTs on this random data and then store them back in Y. And we're going to do that for N iterations. So real simple concept here. Just in each iteration, create a new random array X and run an FFT on it. The big deal about this snippet of code is this function device. Device lets you change GPUs in your code. So if you have 4 GPUs, you can round robin between the 0th, 1st, 2nd, and 3rd GPU and queue up all of those GPUs with all of these randomly or random number vector X's and do all those FFTs and sort of evenly parcelate out the body of this loop out to the various GPUs that exist. So what really happens here is, the very first thing says, okay, in this body of the loop, I'm going to assign this particular iteration to a device and the device is simply a mod of I to be 0, 1, 2, or 3 in the case of 4 GPUs in your system. ArrayFire automatically does the mod based on the iteration count and will sort of fan this computation out to the GPUs evenly. And then, so that's the first line. You assign it to a GPU, and then you're doing your standard ArrayFire computation. At the end of the loop, all GPUs are now computing simultaneously until they're all done. So the loop body queues up a bunch of work for many GPUs to try to accomplish. All those GPUs get all this workload assigned to them. They start crunching the data, and then the program either is able to continue, or if it needs a result from the queued up work, then it will halt and automatically halt operation and wait for the results of the queued up work to return before proceeding. That's part of the lazy evaluation optimizations that ArrayFire makes, which you can learn more in the ArrayFire documentation. So that was the second feature of an array, is that you can run it on multiple GPUs very simply with that device function. The third and probably most important value of using ArrayFire is that there are hundreds of functions which have been pre-optimized for you to use on the GPU. Whenever you have an array, you have access to reductions, linear algebra, convolutions, FFTs, image processing, interpolations, sorting. There are literally hundreds and hundreds of highly optimized and tuned functions for a variety of types, matrix sizes, kernel sizes, and use cases. Again, this body of functions is the reason why so many organizations have achieved success with our tools to date, is that we have so many functions that are available. And they're plenty fast. If you compare ArrayFire to MKL, Eigen, IPP, or Armadillo, in all cases, it's much, much faster. In this case, we're comparing to a high-end Xeon versus a Tesla, NVIDIA Tesla GPU. And I'm just going to run through here. Matrix multiply and summation, a reduction for various vector lengths or matrix sizes are shared in these slides. Similarly, convolutions, both 1D and 2D convolutions, and cumulative sums or sorting operations are also much faster on the GPU. So really what it comes down to for people who are considering ArrayFire is, you could go the painful route, which is maintain and develop documentation, testing infrastructure, and low-level code development for CUDA or OpenCL yourself, in which case the development time goes way up and the cost of development goes up because of that. Or you can use a library. In the case of ArrayFire, it's actually free for most users, and I'll talk about that in a moment. You can use ArrayFire building block functions, program at a higher level that's more maintainable, more readable, and doesn't require the hassles of low-level development efforts. You can save 95% of your time and the cost of porting your algorithms, and free up your developers to focus really on the more important parts of the application development process. It's also very easy to maintain. The nice thing about coding with ArrayFire is the ArrayFire functions and the ArrayFire notation is impervious to fluctuations in hardware vendors or hardware programming paradigms. It's sufficiently high level that any changes to CUDA or OpenCL APIs underneath the hood are swept under the rug of the ArrayFire high-level expression, so that you simply will be able to update your ArrayFire library versions and get access to the latest hardware features. For instance, we expect that NVIDIA will release its new Kepler architecture within the next year or so. When they do so, ArrayFire users will not have to do anything to change any existing ArrayFire code. all they'll have to do is install the latest version of ArrayFire and automatically get to tap into the features of the Kepler architecture. And finally, the last slide is on the ArrayFire licensing. We're pleased that today it's largely free. We have a free version that's a shared license. It's being used by many, many people. It's fully functional, full performance, no limitations whatsoever on data types or just the breadth of things that you can do with it. The one big limitation is it's only one GPU is available through this shared license. So if you do want to scale up to a cluster, that's going to require a commercial version down the road. But to get started with a single GPU, there's no investment required on your part. It does require an internet connection to the shared license server. Early next year, we are going to launch a commercial version, which will make available a dedicated license so that you don't need to have an internet connection for that shared license server, and that'll be coming soon. And with that, I'm going to transition to Gallagher Pryor. Any questions? Yes, and I'd like to let you know that the chat line is open. We're monitoring it. If you have any questions that you would like to ask during this webinar, there's sufficiently many of you that it's too difficult to have everybody be able to talk, but through the chat panel, we will receive your messages and be able to communicate with you in that manner. And now I'm going to pass the control to Gallagher Pryor, who's going to run us through some demos of Maximus applications.
All right, hi everybody. So what I'm going to do now is go through and do a demo of 4 of our example applications. And the major points that I want to make about this is that the graphics are pretty robust in ArrayFire. They're fast, and they're very well integrated with the compute side of things in ArrayFire. There we go. All right, so the first thing I'm going to do is I'm going to run a little simple example called Blip, just to give you an idea. Yeah. There we go. Sorry, I had some sharing issues. But just a very simple application called Blip that'll give you an idea of what the graphics are capable of in ArrayFire. So I don't know if everybody could see this, but here we have subplotting going on, plots going on, 3D surface rendering going on, and all this is being computed in real time on the GPU. And the beautiful thing about ArrayFire's graphics is that you can really get in and you can interact with your data. You can zoom in, zoom out, see exactly what's happening, and it's not complicated to code any of this stuff at all. So let's just take a moment to take a look at the code that enables this Blip example. If I can find it. Here we go. So Blip is actually pretty small. There's some GPU computing going on. That's computing sort of a sigmoid function modulated by cosine, and that's not really important. What's really important here is the graphics calls. All that's necessary in order to get those great graphics that I was showing you are these commands right here. So subfigure gives you sort of a subplot within the window, and then here I'm asking it to give me a subplot that's for a 2-panel window across and 1 panel up and down, and then I'm just plotting 3D. That gives me my surface plot, and then another surface subfigure gives me my plot, and then another subfigure that gives me the other plot, and then finally an image plot in the lower right-hand corner. And the interesting thing about this is that all these commands are non-blocking. What's happening in the background is that there's a separate graphics thread with its own OpenGL context, and all these commands are getting queued up. So what this is designed to do is enable you to write a piece of software that does compute and tries to use as many GPU resources as possible to do what the science that you care about, and then use whatever's left over to give you an idea of what's actually going on in your code or what's really going on with your science. And that's really the key idea behind Maximus, is being able to do the compute and the display on the card without ever having to bring the data back to the device. So I'm going to go through a couple other examples, if I can find those. Here's an optical flow example. Simple horn chunk optical flow between two images. The flow fields are being depicted on the right-hand side, and the source and target images are displayed on the left-hand side. Let's run that again. There we go. And if I go take a look at the code for this, let's see, examples. Leave miscellaneous. Examples. Oh, I missed it. If we go take a look at the optical flow code, take a look at the source header file real quick. Here we're actually computing the optical flow in this optical flow demo function. But then what really matters here is, the display. All we're doing, again, subfigure, IMG plot, subfigure, IMG plot. Very simple commands. You don't have to know anything fancy in order to do great graphics with ArrayFire. Next, simulation of the shallow water equations. This one's a cute one. So here we're showing image S or IMG plot over on the left, and the other hand, or on the right-hand side, we're showing a scatter plot of the gradients just plotted against each other to look cool. You can zoom in and out of this, and turn it around, look at it as it's computing, and also zoom in on the image plot and see what's going on. Next, a very simple vortex example. This just shows the vortex of particles. It runs pretty quickly, and it's just a scatter plot. And again, the entire idea behind all this is that all the compute is done on the card, and as well as the visualization, not having to bring anything else back from the host. But yeah, 2 cards. Okay. And to prove that we actually have 2 cards in the machine, oops. You can actually get information about your GPUs through ArrayFire quite easily. You can see that we have a Tesla C2050 doing a compute, and then a GPU 1 is a Quadro with 2000 doing visualization. So they're both working in tandem to get you great graphics and also high compute speeds. So that concludes the demos. I think I'm going to turn things over to John Melanakos again and see if we can field any questions.
Okay. If you'd, I'm going to start answering some questions in the chat window here. Okay. First question is to show a little bit more code example, and I think they want to get a feel for the compute on some of those. Let's see, which one was that? The shallow water?
Okay.
One second. I'll pass it to Gallagher. He's going to show some compute code that was used in that simulation he showed.
All right, so go take a look at the shallow water example real quick. So So let's divide the code up into two pieces. So there's the compute and there's the visualization. So the computation for the shallow water example, it just actually comes down to a series of convolutions. So here we are here we're defining arrays and then doing convolutions to do the shallow water simulation. And then the visualization is accomplished just with subfigure and IMG plot and subfigure points. And you can give titles to your plots, just like you could give titles in other applications as well. And if you look through this, I mean, it's actually quite straightforward. I mean, there are constants defined here. There are arrays defined here. Just vectorized coding all throughout. And to actually do the compute, the variable we actually care about computing is eta. And it's being ETAP and eta are just being computed very, very simply using just convolutions here. And it just slides right in perfectly with the way scalars are handled as well.
Okay, there's another question here about how do you integrate other CUDA or OpenCL code with ArrayFire? Maybe you can go ahead and answer that one as well.
Yeah, so the wonderful thing about this is that we're not trying to cover up CUDA in any sort of way. In order to integrate, or if you wanted to integrate some CUDA code with this code, it would just be a simple matter of just going ahead and writing the whoops, I don't have my Emacs key bindings on. Just go ahead and write your kernels in line with the code and then call them in with the code too. So there's an example of this called PyCUDA I can show you. So here's a case where we're actually doing CUDA calls along with ArrayFire. So this is using the ArrayFire C interface that we showed in our presentation. And you see that even though we're using ArrayFire, you can call CUDA just like you would normally. And then, so the way this code works is that we generate two random samples of 1E7 in length on the unit interval, and then we compute how many of those ended up inside the unit circle, or I guess the unit quarter circle. And then from there we use ArrayFire to compute a sum. So before there's a CUDA call, and then we compute a sum, and then finally we end up with a value of pi computed over on the host.
Okay, there's another question about how does ArrayFire compare to Magma. And for those of you who don't know, Magma is I believe it's an open source project to do some linear algebra type functionality. I believe it's modeled after the LAPAC interface. And ArrayFire is a broader set of functions than just linear algebra functions. It does contain many linear algebra functions and actually subsumes and leverages some linear algebra libraries. The one that we use in ArrayFire is actually CULA. CULA is a commercially supported library from EM Photonics, and in all the tests that we've run, CULA both outperforms and has more features than Magma. So that's available for you. But in general, the goal with ArrayFire is to provide a higher level, comprehensive set of functions, both linear algebra and otherwise. And we leverage, for many of those functions, other libraries, the best libraries for GPU computing in the community, for BLAS, FFT, LAPAC, even some other functions such as sorting. We are able to leverage libraries both from NVIDIA as well as AMD, as well as EM Photonics and others. And so ArrayFire really does contain the very best that's available in GPU computing from all the various sources that are available today. Let's see. I think okay. There's a question: is the Maximus features of ArrayFire part of the free ArrayFire? And yes, the Maximus features are part of the free version of ArrayFire. Again, that's you can download it from our homepage, AccelerEyes.com. When you download and install ArrayFire, you don't need any separate license file. The license file is already built into the product. You simply need to be connected to the internet so that the software can automatically check out one of these shared licenses from the shared license server that's available for the free version. And when you do that, you will get every feature available with ArrayFire except for the features to scale out to multiple GPUs. You'll be limited to one GPU, but you'll be able to do everything that is available on that one GPU. And I should mention, in the case of visualization applications, we limit the GPUs for compute, but in the case of visualization applications such as this Maximus scenario where we were using the Tesla to do the compute, but using the Quadro to do visualization, that's fine. That will still work. We only are limiting the GPUs upon which you can define array data types. And those array data types, in this case, in all the examples we've shown today, the array data types have been defined and exist only on the Tesla. And then it's only in the OpenGL visualization commands as part of the separate thread, this graphics thread, that those have gone over to the Quadro, but that's not part of the limitations of multi-GPU computing. Okay. There's a question about all we've shown today is CUDA-based NVIDIA execution. How does this compare to our OpenCL version? And I should say that our CUDA, we have two different versions of ArrayFire that are separately downloadable. One is CUDA-based, and the other is OpenCL-based. The CUDA-based version, of course, runs on NVIDIA GPUs only. The OpenCL-based version runs on AMD's ATI GPUs. It also runs on the CPU, whether it be an AMD CPU or an Intel CPU, and it runs really on any OpenCL supported device. The CUDA version has been around longer. It's built, our company has been partners with NVIDIA longer, and therefore is much more mature with many more features. The OpenCL version is in a much more of a beta state. Fewer functions are available in the OpenCL version, but the advantage, of course, is that it's not bound to any single GPU hardware vendor. It's more neutral. And over time, we expect the OpenCL version to mature and have all the same features as the CUDA version does today. And there's a question asking about performance relative between the two. And I should say that again, the main difference that we've noticed between the two is the feature set, that the CUDA version has many more features than the OpenCL version. But performance-wise, there are some cases in which the OpenCL is faster, and there are other cases in which the CUDA version is faster. And so it's something that, it's hard to make a blanket statement about, but certainly for your algorithm, we invite you to try both. The nice thing about using ArrayFire is it doesn't matter. It's the same code. As long as you're using functions that are supported by both the OpenCL version and the CUDA version, your code will run without any modification on either the CUDA-based device or OpenCL-based device. Okay, with that, I think that answers all the questions that I've received. We'd like to thank you for your attention. We'll be holding webinars on the 15th day of every month in 2012. And so look on our blog, blog.AccelerEyes.com, for announcements of these webinars. And we look forward to working with you in the future. The other thing to mention is that we are in the mode of offering GPU consulting or GPU services. If you're interested in those services, or if you would like to have some free consultation, you can email us at sales@AccelerEyes.com, and we'll be happy to provide you with any starter advice that we can. Thank you very much.